Welcome everyone to the IFI monthly seminar. I'm Peter Sadowski. I'm Associate Professor of Computer Science here at University of Hawaii Manoa, and we're presenting William Rudman, a PhD student in the Computer Science Department at Brown University and a member of the Joint Health NLP Lab at Brown and Tübingen University. And William is going to talk on the interpretability of large language models. Thanks for coming, William.
Thank you guys for having me. I'm excited to be here and talk about some of the research that I've been doing in this space. There we go. So yeah, as Professor Sadowski said, my name is William Rudman, and I'm a fourth-year PhD student in computer science at Brown. So I'm a member of the Health NLP at Brown and also at Tübingen, which is kind of weird to have this kind of joint lab, but it's because my advisor left to University of Tübingen. So today I'm going to talk really focusing on interpretability in large language models, as well as kind of touching on some applications in a clinical setting. So if we think of this spectrum between pure kind of clinical research and clinical AI, and more this spectrum towards core NLP research. So clinical AI would be applying AI tools to study a clinical setting. So a good example would be fine-tuning a CNN to detect abnormalities in, say, like a CT scan, where this kind of core AI research would be developing foundational language models. Somewhere in the middle, we have studies like Clinical BERT that use these core kind of NLP concepts in a way that is adapted for a general purpose clinical setting. So this talk lies somewhere in between here on the spectrum, and much more towards this core NLP research. So I know this is going to be more of a technical talk, so please feel free to interrupt and ask me any questions that you have. If there's any terminology or any of the models that I talked about that you're not as familiar with, please stop, and I'm happy to go over them. So before going into my kind of interpretability work, I want to explain what is the state of clinical natural language processing models, as well as going over why interpretability is important at all. Like, why do we want to generate these explanations and understand what's happening with these models? So the first kind of foundational tailor-made large language models for clinical settings is this model called Clinical BERT, like as I just mentioned. So what these authors do is they take this large language model transformer encoder, they take this architecture, and then they pre-train it from scratch on these clinical notes. So that way we don't have as much of this domain shift from a books corpus to clinical notes. And these transformer encoder language models have really dominated the state of the art in terms of classification tasks and predicting patient outcomes from a clinical note. Now, although these models have become increasingly important and more common in a clinical context, there are still some really heavy limitations to how they can be used in a clinical context due to their lack of interpretability. So we really don't understand how these models reason about input text and make decisions on downstream tasks, and this is something that limits clinical applications. So in particular, a 2018 study found that clinicians tend to override diagnostic tools in at least 25% of the cases. So these authors developed a model that had really high performance, and authors and clinicians tended to reject the diagnosis of these models. Now, even though some of these clinical diagnostic tools can be underutilized, given an explanation, people in general tend to overtrust AI decisions. So when we have some notion of how a model is making its decisions, then people tend to have a limited ability to detect model errors. So for example, this study looked at predicting house prices in New York City, and one group of participants received a model where they had some explanation of this model is predicting a price based off of the number of bedrooms times the number of bathrooms in square feet. Now this apartment deemed apartment 12 here is a really unconventional and undesirable configuration where you only have one bedroom and 3 bathrooms. Yet when people saw this explanation of the price, they were more hesitant to adjust their expectations of what this price should be, and they tended to trust this model's this decision, even in the face of an obvious error or oversight. And in a clinical setting, generating explanations that can foster this overtrust, if these explanations aren't robust, then this can lead to worse patient outcomes instead of improving patient outcomes, which is the goal of these clinical tools. So what tools in NLP do we have to try to reason about how a model structures its embedding space, the types of knowledge that it encodes inherently, and also how models adapt their embedding spaces to fine-tune for specific tasks? And the most common way to study these large language models is through this technique called probing. So if we think of a standard fine-tuning NLP pipeline where we have this input text that's projected in this high dimensional space by our favorite transformer model, you output this token, the sequence embedding in the CLS token, and it's typically fed through some classifier to make some downstream decision. And the way that probes work is they look at individual layers and individual embedding spaces of different layers of our model, and they train a much smaller neural network to try to test for the presence of different human interpretable concepts. Now, this seems a little counterintuitive to explain a black box tool, a larger black box tool with a smaller black box tool. However, these probing techniques have been really revolutionary in shaping how people approach large language models and the types of knowledge that they encode in their embedding space. So one of the seminal works in this field studied BERT, which is, if you're unfamiliar with BERT, is kind of the first large language model that came out, or at least the first transformer large language model. And what the study did using probing, they found that early layers of BERT that are trained to do a task are able to encode high-level syntactic information. And by that, I mean they're able to extract things like part of speech of a given token without being trained to do so. Now, using probing as well, they looked at later layers in the network and found that in later layers, you're able to encode higher level and more difficult tasks, such as extracting some semantic information about a given sentence, or even performing difficult tasks like co-reference resolution, where you're resolving ambiguous pronouns and like object-verb agreement. Now, even though these probing techniques have been really useful in shaping the way that we think about models, and also shaping our understanding how models go from higher level, more like I guess low level encodings to more rich information, these probing models are subject to what's called interpretability illusions. Now, the paper that first kind of came up with this concept of an interpretability illusion found that probes and studies that look at individual neurons spuriously appear to be encoding interpretable concepts. And so what they did is they took some randomized inputs, completely randomized inputs, and they trained a probe to detect different human interpretable concepts. And these probes would find interpretable concepts even though these inputs had absolutely no semantic or no meaning. In addition to this subject to interpretability illusions, probes also don't have any causal prediction power. And by that, what I mean is even if a probe accurately identifies certain high-level concepts in a model, we have no way of knowing that this model is actually using this information for its downstream decision. So really where we're at is people who research NLP don't really have a good concept of how these embedding spaces are structured and the types of knowledge that they contain. So the first kind of aim of my core research here is to look at describing geometric properties of these large language models. So before we go about how these models reason about different task-specific information, we need to have a baseline of how are these embeddings structured. So once we look at how these embeddings are structured, we then want to have a deeper understanding of how the geometry of a given network can correspond to downstream model performance. And lastly, we want to leverage our knowledge of the geometric structure of these large language model hidden states in order to interpret how models make decisions and identify how models store task-specific information as they adapt their embeddings for different tasks. So I'll first start by talking about a paper that I developed with some of my colleagues at Brown called ISOScore. And what ISOScore does is it measures this property called isotropy, which I'll cover in a little bit, but really we're looking at how well a giving embedding space utilizes, or giving embedding uses a full vector space. So people have tried to study the geometry of these large language models and how they organize their embedding space before. And the dominant hypothesis is that these large language models occupy a narrow cone in space. And so that, I mean, the actual shape of these textual embeddings is something that's closer to a cone and only utilizes a couple of the dimensions in space and doesn't uniformly utilize all of the dimensions. So people have used average random cosine similarity to argue that these large language model embeddings lack this property of isotropy, or this uniform utilization of the space. And there have been several studies that have argued that this geometry of occupying a narrow cone is a fundamental limitation of a transformer large language model architecture. So studies have argued that this geometry is undesirable in that it limits the expressiveness of textual embeddings and how rich of knowledge these embeddings can encode. And it actively hurts downstream performance on a variety of both interpretability and classification tasks. And by obscuring interpretability, people have argued that these large language models no longer have semantically meaningful directions in space, like some previous, more classic NLP counterparts have. And by that, I mean previous NLP models have had some semblance of there's a direction in space that encodes similar concepts. So there'd be a direction in space that tends to embed things like animals in one space, and plants in another object of another direction of the space. And this is completely obscured in these large language models due to this geometry. Now, if you're going to take away one core definition from this talk, it's this concept of isotropy that we use to study the distribution of this high dimensional vector space that these large language models occupy. Now, a distribution is isotropic if the variance in the data is uniformly distributed. And what this means in practice is that the covariance matrix is proportional to the identity matrix. So here we have a line, a circle, and a sphere embedded into a three-dimensional space. And this kind of runs the spectrum between a space that has no property of isotropy or is anisotropic because it only utilizes a single dimension, something that's somewhat isotropic in that it utilizes two of the dimensions available in vector space. And then here we have a sphere that uniformly utilizes all of the dimensions in space. So I know this can be a little maybe math heavy and conceptual. So I just wanted to check in and see if there's any questions about any of the stuff I've covered so far.
What is the typical dimensionality of the space you're talking about?
Yeah, great question. So it can differ depending on the language model. So for really small models, you're going to have a very minimum of 500 plus dimensions. A really common choice is 768 or 1012. But when you go to some of the biggest available models, like think like a GPT-4, you could have tens of thousands of dimensions in space. So it's extremely high dimensional.
And is this tied to the particular layer in the transformer architecture? Like, is it the output of the transformer layer or the output of the MLP layer? Does it matter?
Yeah, so when we're talking about the hidden states of the models, we're focusing on the MLP layer since they occupy a vast majority of the architecture. But you can hypothetically do this on the outputs of the attention layers as well. All right, yeah, thank you. So people have used this metric of average random cosine similarity to make this argument that embedding models only occupy a few of their dimensions in space. And they do this by saying, well, the angle between these two on average, the angle between the 2 points is really small, and the cosine similarity is something that approaches 1. And they use this to make comments on the full structure of the space. But a really simple way to see that cosine similarity doesn't measure isotropy at all is to just simply apply a zero mean transform. Now, when we had this really small angle in space, now that we have zero mean, the angle between them is 180 degrees, and consequently, the average random cosine similarity now goes down to 0, which people would say is an isotropic space. But given that isotropy is a property of the variance of the point cloud, and we can see that applying this transformation doesn't do anything to the shape and the utilization of the space, we can say that cosine similarity maybe doesn't measure isotropy in the way that people have argued. So in order to fix this, we propose our metric isoscore. Now, this is developed directly from the definition of the covariance matrix. I won't cover the full mathematical detail, but if you want to have slides later on that kind of walk through this. But the intuition behind it is that we're defining a distance metric almost on the covariance matrix of an input distribution and the covariance matrix of what would be a uniformly isotropic space, which would be something that's proportional to the identity matrix. And we developed, and we can just propose a metric and say that it's doing exactly what we're doing. So we develop a suite of 6 rigorous tests to ensure, or at least outline, minimal essential conditions for something to be accurately measuring the property of isotropy and commenting on the kind of full geometry and distribution of the space. And kind of concerningly, we find that average random cosine similarity fails on a vast majority of these minimal essential conditions where isoscore successfully passes all of these. And so this kind of calls into question a lot of these claims where people have argued that isotropy is beneficial for model performance and interpretability. So, and also you may be wondering, are these models actually isotropic at all, or are they not isotropic? And kind of interestingly, in a right for the wrong reason way, we see that models are actually even less isotropic than previously thought. So if we look at this purple line here, these tend to be much lower isotropy estimates than previous methods for measuring this. So now that we've developed a metric that can accurately quantify some geometric properties of these models, we now want to challenge these conceptions that isotropy is good for model performance, or really kind of ask the question of what is a desirable geometry for these embedding spaces to occupy. And a really simple way that we can do this is by building a regularization algorithm. We just take isoscore and we use it to adjust the geometry in whatever way that we want. So we ran into 2 fundamental and non-negotiable errors in doing this. And the first thing that we find is that isoscore will systematically underestimate isotropy values when the number of samples is less than the dimensionality of the vector space. And this is something that actually isn't very surprising. So since isoscore is a function on the covariance matrix of a distribution, if you don't have enough samples to accurately define a covariance matrix, then we have difficulties in estimating the true distribution of the space. And secondly, we find that isoscore is a non-differentiable function. So we work to both make a new metric that preserves all the properties of isoscore, is stable for mini batch computations, and it can be used in a regularization algorithm to shape the geometry of these networks. And the first way that we do this is to apply something called regularized discriminant analysis, where essentially we take a known stable covariance matrix and combine it with this sample matrix. And additionally, instead of viewing by measuring the geometries of this space through a covariance matrix structure, we look at isotropy in terms of principal components. So here, a maximally isotropic space is when all of the principal components of your data are uniformly distributed, and a minimally isotropic space is when only a single dimension or a single principal component explains all of the variance of your data. And we find that in the limit, so given a sufficient number of samples, ISO score approximates ISO score star, and it equals ISO score when no discriminant analysis is performed. So here, if we think of a sample point cloud, we have 768 dimensions. We say that when no discriminant analysis performed at 0, the isotropy values are systematically underestimated. But just by simply performing this addition of a known covariance matrix, we're able to have a much better intuition about the geometry of this space. And if you're unfamiliar with what regularization algorithm is, what we do is we take our ISO score star penalty that we compute from different hidden states of the model, and we do this as a global isotropy penalty, and we combine it with standard cross entropy loss for fine tuning. And we call this our I star loss. So it's ISO score based stable anisotropic regularization. And kind of the key thing that we want to look at here is this tuning parameter lambda. So as we increase the tuning parameter and we make it positive, we can increase isotropy. So this is going to shape the distribution of the principal components and making them more flat. And if we use a negative tuning parameter here, we're decreasing isotropy in the space and we're compressing these representations into an even lower dimensional space. So they're using even less dimensions in space. So what we find using a robust method for measuring isotropy is that there is a negative correlation between isotropy and performance. So this geometric structure that people have argued that utilizing all the dimensions in space is beneficial for your model, we actually show that as we increase isotropy values, performance tends to decrease. And we do this by shaping our network with the different values of this tuning parameter. And not only do we see this correlation between low isotropy values and high performance, when we fine-tune networks using ISAR regularization with negative tuning parameters, we see across an average of 9 different NLP benchmarks that we tend to have improved performance by further decreasing isotropy in space. And additionally, we compared our baseline fine-tuning with cosine similarity regularization, even though it doesn't measure an impacted geometry. It's something that people have done, so we wanted to make sure that we are covering our bases and are actually studying these properties of isotropy and kind of couching this in the previous literature a little bit more. So given our knowledge of the structure of large language models, we want to start to reason about if these geometric formulations are important to the model fine-tuning, and compressing into even smaller dimensions is beneficial for model performance. We next want to look at this claim that this geometry inherently reduces our ability to interpret model decisions and also obscures how models store task-specific information. So here we're looking at this phenomenon called outlier dimensions in these large language models. So these outlier dimensions are these dimensions with really, really high variance, and formally we consider a dimension an outlier if the variance in a given dimension is 5 times larger than the average variance of the space. So here we plot sentence embeddings from GPT-2 on the SST2 validation dataset. And the way to interpret these graphs is for a given sentence, we have a 768 dimensional vector. And what these plots show is we plot on the Y axis, we plot the value of the dimension at the individual component of that vector. So if we take a collection of a bunch of sentences, we can have a semblance of the distribution of variance, or the distribution of variance and also magnitude in a given large language model embedding space. And here, these dimensions with really high spread are exactly these outlier dimensions. Now, the literature agrees on the formulation of these outlier dimensions, and people have argued that the origins of these outliers come from token imbalance in pre-training data. So if we think of the distribution of word frequencies in the English language, we have a ZIF distributed function where a really small number of words are really, really highly frequent, and there's a large number of completely non-frequent and rare words. And so the idea is that models are taking this distribution where you have a lot of points being, or a small number of points being highly frequent, and this kind of shapes the distribution of this output. And people have found that these outlier dimensions, you can extract frequency information from the pre-training corpus directly from the value of these outlier dimensions here. Now, similarly to works on isotropy, people have argued that these outlier dimensions are fundamentally bad for these large language models, and that by removing these models, we can improve, removing these outlier dimensions, we can improve model performance on downstream tasks, as well as improve our ability to interpret model decisions. So the focus of this section is to look at how fine-tuning impacts these outlier dimensions. And one of the key things that we find here is that these same outlier dimensions that are present in pre-training data persist during the fine-tuning process. So we can see that these models are in some ways adapting these small set of outlier dimensions, and they are reusing them in the, or they're relying on them in the downstream fine-tuning task. And we even see the emergence of some outliers in models where the variance is significantly larger than it was in the pre-training space. And not only do we have this kind of same set of pre-training outlier dimensions emerging in fine-tuning tasks, we also find that these same set of outliers are adapted for a variety of different downstream tasks in random seeds. So here, when we look at the dimension frequency, or the dimension index of a given large language model, and on the x-axis, we have the frequency with which it's an outlier dimension. So the variance in that dimension is 5 times larger than the global space. And what we see is that in models like Roberta and GPT-2 in particular, there are dimensions that are always outliers regardless of any task or a random seed or any training configuration. So given that these outlier dimensions are persistent across different tasks, and previous work that's shown that anisotropy is, or this lack of isotropy is beneficial for model representations, we want to test the hypothesis that these outliers are beneficial to the training procedure of these models. And so we do that by learning a really simple linear threshold on a given individual dimension. So here we're looking at one-dimensional subspaces in these language model representations. And instead of feeding a full large vector into a classification head to make a downstream decision, we want to look at an individual one-dimensional subspace or a one-dimensional basis dimension and learn a really simple linear threshold. And so the way that we do this is we choose the largest outlier in training, and then we calculate the mean of that, and then we brute force iterate through a few values to learn a decision rule. So our decision rule now is for a given input, we look at the value of the model in this individual outlier dimension, and we predict 1 if it's above this threshold, or 2 if it's below this threshold. And for simplicity for this task, we just look at 5 different binary classification NLP benchmark tasks. And remarkably, we find that in several models that we can complete downstream tasks using a linear threshold on an individual dimension. And particularly in GPT-2, we find that on average across these 5 NLP benchmarks, the average performance decrease between a full model representations and a linear threshold and the largest outlier dimension is only roughly 3% or less than 3%. Now, why this this seems useful for GPT-2, and that we can find these individual subspaces that encode task-specific knowledge. If we look at QNLI, we see a big discrepancy between models that are able to encode task-specific knowledge in the single largest outlier dimensions and places where models are unable to encode this task-specific knowledge. In particular, looking at Pythia 410, there's no performance decrease between feeding full representations into a further classification head versus taking the value of a single dimension in space and learning a linear threshold. However, in Roberta, we doing the same procedure on the largest outlier dimension, we see a 35% decrease in performance. So we wanted to explore this a little bit more and say, okay, if these models, if outlier dimensions seem to be really important for these encoder these transformer decoder models like Pythia and GPT-2, how are these encoder models like BERT and Distilbert and Roberta storing task-specific knowledge? And so we do this by extending our linear threshold analysis. So instead of looking at just the largest individual outlier dimension, we apply this to all dimensions in vector space. And so the discrepancy in performance for QNLI for like BERT and Roberta comes in these dimensions right here, where you have really, really high variance, but low performance. So if we look at this red line right here, that's the threshold for whether something is considered an outlier dimension. And we see a really strong correlation between an individual dimension's ability to store task-specific information and its variance in that given dimension. Now, previous studies have typically been limited to looking at outlier dimensions in BERT and Roberta, but if we expand it to other models, we see that even the largest outlier dimensions in some of these transformer models encode enough task-specific information to complete a downstream task with high success rate. Now, it's nice to know that these models are adapting these small set of outlier dimensions and are storing task-specific knowledge in them, but that doesn't necessarily imply that they're using this task-specific knowledge to make or they're using this knowledge from a one-dimensional subspace to make the model predictions. So in order to verify this, or at least taking a step towards verifying this, we run a simple ablation experiment. So if we consider our standard pipeline where we have our text, extract our CLS tokens, and then feed it into a classifier, we apply an ablation mask where we zero out information from individual dimensions. So we take dimensions and we set that representation to 0 before feeding it into a classifier, and then we measure the performance outcome. So we apply our ablation mask iteratively, meaning that we increase the number of zeros present in the ablation mask, and we choose how we grow our ablation mask in 2 separate ways. So in red, what we do here is we iteratively ablate dimensions in order of variance. So we start by ablating the highest variance dimension in each step. And what we find is, particularly for these 3 tasks in GPT-2, that ablating an individual dimension can completely cause performance to decay. So in the case of MRPC, we see full model representations get 80%, but ablating an individual dimension brings it down closer to random performance. And on the other hand, what we find when we ablate dimensions in terms of small variance, we can complete downstream tasks with a really small number of non-zero dimensions. We can ablate over 700 of these dimensions before feeding into the classifier, and we can still complete the task with high performance. Now, we use this to make an argument that these task-specific knowledge that's stored in these individual dimensions is being reused and relied on and dominating the model decision-making process. So what kind of the next step that we want to do is we take our understanding of how large language models work, the geometry of their embedding space and how they adapt to fine-tuning tasks, and we want to apply it to a clinical setting that we're working on. So I'm working on a part of a grant that aims to detect child abuse from clinical notes and patient demographic and diagnostic features. So we have a patient cohort of roughly 4,300 patients between 0 and 5 that present to the emergency department with a fracture diagnosis. And of these 4,300 patients, we have roughly 400, or we have exactly 447 patients with a child abuse consult. Now, this child abuse consult isn't necessarily an abuse diagnosis. There's at least a threshold of the fracture presentation of this child was at least concerning for abuse. And the way that we build our model is we have a clinical BERT backbone. So we use this clinical BERT transformer language model to extract text features from the emergency department note. And then we also have a separate stream that processes the demographic and diagnostic features like ICD-10 codes and age and sex. And we then use some cross-modality encoder to infuse this text model with the demographic information. So our model is aware of the full kind of scope of information that's present in a patient encounter. And then we then use a classifier to predict whether at least a concern for abuse is present in the patient presentation. Now, given this really highly imbalanced data structure, before training our model, we downsample to a set of 500 patients where there's no concern for abuse and 447 patients that had an abuse consult. And using our multimodal model, we're able to accurately identify cases that are concerning for abuse in 83% of the time and have an F1 score of 81. Now, we've been kind of tweaking this a little bit, and we can have our accuracy be really, really high if we have more data samples, but the F1 scores start to kind of drop off a little bit if we do that. So what we wanted to do here, so not only do we want to build a clinical model for detecting the presence of child abuse from ED clinician notes and some demographic features, we also want to aim at looking at how these models store this diagnostic information. So the first step towards doing that is rerunning these linear thresholding experiments to test whether these clinical models that are trained on a completely different domain of data still have the same types of properties as general purpose large language models. In applying our one-dimensional linear analysis, we see that there are dimensions, individual outlier dimensions in space that encode this diagnostic information. And this model is relying on these individual outliers, just like traditional large language model fine-tuning does. Now, the real kind of larger goal and kind of the open-ended work that we're doing right now is we want to use our geometric knowledge and our knowledge of where in the model task-specific information is stored to then start to generate some types of explanations as to why a model is behaving in a certain way. Now, one of the types of analysis that we're working on is applying this new technique in mechanistic interpretability called circuit analysis. And what circuit analysis does is it tries to reverse engineer an algorithm. So it tries to reverse engineer the decision-making process of these models and find where exactly in the model these models are representing certain human interpretable concepts and how they're combining these concepts to make a downstream decision. And the way that we want to expand this is instead of just looking at outputs and these like larger outputs, we want to look at how different components of our model impact this individual outlier dimension that we know is responsible for the classification decision of the model. And the general really kind of goal of this is to, given a fine-tuned model that performs well on a downstream task, we want to try to develop some type of decision tree style explanation and clinical decision rule directly from these clinical models. And we also want to make sure that these clinical models aren't just picking up on spurious correlations in the input text to make a decision. So if you have 4 kind of things to take away from the talk today, the things that I want you to think about are that representations from large language models are dominated by these small sets of outliers. And there is this negative correlation between isotropy and downstream performance. So the way that these models occupy their embedding space is influential both for their performance as well as coming up with ways that we can interpret these models. So for example, we see that when fine-tuning, LLMs adapt the same small set of outlier dimensions to store task-specific knowledge regardless of the task that you're looking at. And not only does this pattern occur in these large language-only trends for these large general-purpose language models, these same trends emerge in these clinical models, which is encouraging that these clinical models that are trained on a completely different domain still have some properties that can be related to the general-purpose models. So I want to take a super quick second to thank everybody in my lab, in particular my advisor, Carson Eickhoff. And if you're interested in this kind of fusion between interpretability work and clinical work, there's a lot of people in my lab that do some really cool work. So some people work on building multimodal clinical models. Some people do some patient-centered information retrieval, so adapting information retrieval models for a clinical setting. And lastly, if you want to learn any more about the 3 projects that I presented today, you can check them out and feel free to email me if you have any questions afterwards as well. So thank you guys for bearing with me through a slightly more technical and theoretical talk, and I'll open up to any questions.
Thank you, William. I have lots of questions on the deep learning stuff, but I will give
awesome.
People a chance to ask their questions first.
All right, sounds good.
If you have any questions, please introduce yourself and ask away.
Yeah. Did you have a question, Ariana?
Yes, I can
go ahead.
start off. I just was wondering on, I think 2 slides previous on your kind of model diagram that you had a demographic output. I was just wondering if you can kind of clarify what that is.
Yeah, of course. So we take so this is inspired by some like vision text language model, like multimodal model stuff. So instead of just putting these like raw demographic features, which would be like the actual ICD-10 code or the actual age of the patient, we feed it through a separate, what we call a demographic encoder. So we feed this vector of the raw demographic information into a smaller neural network. Then the output of that neural network is then used to infuse the text model with demographic information. So it's just a way to have a richer representation of these demographic features instead of just concatenating raw demographic values into a network. Thanks.
So there's a talk from Batong Win in the chat.
So yeah. So I don't know if I understand what you mean by treating NA values in the model. Can you maybe clarify so I can answer your question better?
Yes, thank you for your job. So in the test data, you maybe have some like missing value. How you transform to 0 value, or what kind of value you transform?
Okay, so for going back to this like ablation mask here, where we are removing information from the model. Is this what you're asking about?
Yeah, before the classifier.
Yeah, okay. So what we do is we have this high dimensional representation of our input sequence, and we take a ablation mask that's the same dimensionality of the space, and it's a 0-1 mask. So in order to remove information from this, we just multiply it by 0. So we don't alter the dimensionality of this representation, but we just set it to 0 to kind of remove any relevant information that that dimension stores.
Oh, okay, thank you. Yeah.
Sorry, hopefully that answered your question. Okay.
Yeah, thank you. I got it.
Hey,
Yeah, go
I
ahead.
had
Go
a
ahead.
quick question. I'm also a PhD student at UH, like Ariana, and I'm mostly working with images and mostly working with contrastive learning. But so one of the general trends that I find with that work is that isotropy is a desirable feature. And
Yeah.
just during your talk, I did a quick lookup, and there was at least one paper that said if you incorporate contrastive objectives with sentence level representation learning, you increase isotropy and it does improve performance. Are
Yeah.
you familiar with that at all? Do you have any intuition why you found that anti-isotropic features are beneficial versus this kind of contrastive result that we see a lot?
Yeah, no, it's a really great question. So you're talking about models like CLIP that use this kind of cosine similarity loss to represent these features in a shared embedding space?
Sure.
Yeah. So the way that these models work is, so you're minimizing this cosine similarity objective between two different embeddings. So if you're measuring isotropy by using cosine similarity, or another common way is something called this partition score, which looks at a approximation of principal components. So if you're minimizing the cosine similarity, you're going to minimize the mean of your data. So one of the graphs that we had for the second project, we looked at stable and isotropic regularization, and we fine-tuned with a cosine similarity regularizer. We show that by minimizing cosine similarity, we don't shape isotropy in space, but minimizing cosine similarity implements a zero mean transform. So it depends on the way in which you're measuring isotropy in these contrastive models. But that's actually something that I'm kind of actively working on right now, is looking at these, applying these types of metrics to contrastive models. So thank you for the question. It's a really, really good and really interesting area of research. Hopefully that
Cool.
answers it a little bit.
Yeah, absolutely. Thank you so much.
Yes. Okay. So the process for selecting our features for the child abuse model. This one is a little bit less of a question for me and more of a question for the people that I work with on this grant. So the way that we selected these features is based directly on some previous literature, as well as input from some of the child abuse specialists that I work with. So essentially, they told me, here are the things that you should include in your model. We did a little bit of correlation analysis to see like what variables are correlated with one another, removed those variables, and then we put these inputs into the demographic feature. But it's also something that's definitely an area to tweak a little bit to see like what are the best features, not only just for explaining variance here, but also explaining model performance.
So one quick question, William. Why not just use dropout to get rid of these outlier features? Because that'll force the model to not rely on a single feature, right?
Yeah, so dropout is heavily used in pre-training of these models. But when you go to evaluate the models, you don't want to do any dropout because you don't. The idea is you don't want to get rid of this information. This ablation mask that we do is, a way to think about it is it is a structured dropout. So during the evaluation phase of the model, where normal dropout is shut off, we're enforcing some of these dimensions to be shut off. And one of the kind of hypotheses that people have as to why we have multiple dimensions that encode task-specific knowledge is that dropout will randomly remove some information. So you need to have multiple backup places to store this.
So I was thinking that dropout would remove those outlier dimensions, right? You would have to have redundant information in the network.
Yeah.
But you're saying that dropout is already used, and still you have like a small select set of features that. Okay. Yeah.
So before, both like throughout the layers of the model and in the pre-training and fine-tuning phase of these models, there are dropout layers through each attention layer, each feed forward layer, and also the output before the classification layer.
And in terms of the interpretability, you know, the analogies that people used to talk about with respect to word to vec,
Yeah,
right?
exactly.
You know, that got a lot of people's attention. Do you have a sense of do these models give you analogies like that, or is word to vec more interpretable than these modern transformer-based language models?
I think you know that's a very deep question. So the first thing that I'll say is, yeah, I think that this idea of directionality is representing some semantic meanings makes these models at least more interpretable in a lot of ways. So we're able to easily kind of reason about like, oh, well, these models may like organize their embedding space in some way. So we can at least understand some properties of these models. But kind of tying it back to the probing, we also, okay, so it's organized in this way, but we still don't necessarily know how these directions are combined in a way to reason about a downstream task. To answer the first part of your question, there is Jack Marullo in my lab actively researches things like this. And so he has found in a recent paper that instead of implementing individual kind of directions in space, that models implement word-to-vec style functions. So you can take this additive vector, you can add it to a given country, and it will output the capital of that country automatically without knowing any information about the task. So there's starting to be some semblance of word-to-vec directionality in meaning space for these large language models, but it appears to be a lot more complicated than just directionality.
Well, I have a related question to Peter's. Has there been any exploration from your group on kind of translating this notion of interpretability for like maybe healthcare professionals with low numeracy that maybe aren't super familiar with, you know, all of these mathematical concepts?
Is that question for me or is it for? Oh, is it for me? Okay, sorry. Sorry, I thought you were asking it to Peter. My bad. Yeah, that's really kind of something that we want to actively work on, and why I am on this team that's looking at these clinical tasks. Like one of the things that I want to do is use some of the clinicians that are on this team to say, okay, we're going to try to generate these explanations from this mathematical sense. We'll maybe try to map them to a little bit more human interpretable, higher level concepts. And one thing we want to do is have the clinicians run this model and see if the explanations make sense and are also useful. So that's going to be kind of step 2 of after we finish this kind of more circuit analysis stuff and have more full explanations that are a little bit less mathematical. We want to kind of see, are these actually useful, or do we get something similar where clinicians override these tools or they trust them too blindly? Yeah, but something definitely will take a lot of work to do.
Do you think in the end that performance will be correlated with interpretability?
Wow, these are really getting theoretical.
Because there's an argument that, you know, in order for the model to be really good, it needs to factor the concepts in such a way that it can make sense of the world, right? And it has to like build a good world model. And it needs to be factorized and somewhat interpretable to do that.
You know, I do think so. I do think there has to be some level of being able to be interpreted. It's just I don't know if we have the tools to really, right now at least, we're starting to develop the tools to learn how models reason from these low-level inputs to high-level abstractions. So yeah, I think that in order for this model to not just be relying on some linguistic prior information or even just kind of exploiting random patterns in the data, yeah, it needs to be able to have a notion of interpretability that we can at least understand a little better. We can at least map our understanding to how a model reasons about different inputs.
Are there questions for William? Okay, I've got one more deep learning question. So, historically, you can argue that a lot of the progress in AI over the last 10, 15 years has been in figuring out tricks to train deep neural networks, because training deep neural networks is hard. A lot of those tricks have to do with just helping the information flow through many layers of the network. So there's been lots of work on like conditioning neural networks, skip connections and ResNets. You can view transformers as part of this because it allows you to send information long distances in a deep network. And so your work on isotropy seems very much connected to this because you're trying to ensure that the representation of your data lives in a space that's smooth and has certain properties. So my question is, have you looked at this isotropy property in deep neural networks without transformers? And is there any connection there to the work that's already been done?
So in terms of not transformers, first of all, yeah, that's a really, really good theoretical question once again. So in terms of non-transformers, there's been a couple papers that have argued that these vision models have a more balanced representations. So if you think about, you're trading a CNN on like MS Coco, like there is some discrepancy between label spaces, but it's not nearly as big as in transformer models. So the distribution of labels, right? So labels are just words when you train these models, is much sharper than the label space of how we tend to train CNNs. But I think a really interesting study would to be looking at the isotropy values of like CNNs versus vision transformers. So is there something inherent about the transformer architecture, the way that we build up this residual stream that favors isotropy or anisotropy, or is it more on the label space? And if it's on the label space, then it would be very difficult to adjust or smooth out the distribution for language models, at least. But something I'm working on right now is exploring these multimodal models, not just for this clinical setting, but we're also looking at a suite of different vision texts. So things like CLIP, things like LexMERT, and we're exploring isotropy values and whether these same types of fine tuning in small dimensions happens there.
Thanks. Any last questions? All right. Well, William, thank you very much again. This has been a great talk. And we hope to see you in person sometime soon.
Yeah, absolutely. I'm in Hawaii for the next 6 months, so reach out. All right, thank you guys so much, and feel free to reach out if you have any other questions. I really appreciate you guys sticking with a little bit more technical and theoretical talk.